Welcome to CCCS122 Discrete Mathematics, and we are continuing with Chapter 7, Discrete Probability. So, suppose there's an experiment in which there are only two possible outcomes, such as tossing a coin. So either an experiment in which an event either happens or doesn't happen, and with no other options. An experiment like that has a special name. It's called a Bernoulli trial. We often also call the two outcomes, we label them success or failure. If P is the probability of the success event and Q is the probability of the other event, the failure, obviously, since there are only two possible outcomes, P plus Q will equal 1. Now, the probability that we'll see K successes when we conduct not one, but N independent Bernoulli trials, meaning N experiments, one after the other, the probability that K of them will see success at the outcome, as the outcome, that probability can be computed like so. And this has its own probability mass function, or called the binomial distribution. I know the one that I showed you was drawn using a stem plot, but in many places you'll also see that probability mass functions are plotted instead of a stem plot, they're plotted as bar graphs, like the one that you see over here. In this one, you can see that the number of outcomes, it seems, is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9. It seems like there are 9 trials being conducted, and the number of successes can be anything between, actually, maybe it's 10, might even be that you have 0 successes. So it seems like there are like 10 Bernoulli trials being conducted, and this binomial distribution is giving you, it's actually not even a true distribution. This is not normalized because these values are not adding up to 1. This is before normalization. All right, so not really a binomial distribution, but this over here, anyhow, this is how we get the probability that K trials will turn out to be successes out of when N trials are conducted. As a proof for this expression that's given in the textbook, I won't go into it here. So this expression for the Bernoulli PMF is given, it's abbreviated like this. B for Bernoulli, K is the number of successes, and 2 parameters that you have to provide is the number of trials that have been conducted, the number of Bernoulli trials that have been conducted, and P, the probability of success. Q, that you see over here, can be found once you know P, of course. So that doesn't have to be provided as a separate parameter. So the Bernoulli function that you see over here is then basically a function of K. Now, often we're interested in the probability of exactly K successes when an experiment is it consists of N independent Bernoulli trials. So, for example, a coin, let's say a coin is biased, and the probability that head shows up is 2 by 3, meaning that the probability that tails shows up is 1 by 3. What is the probability of exactly 4 heads coming up when the coin is tossed 7 times? So 7 is the number of trials being conducted. We're interested in how many times K, or the number of successes, is 4. P is equal to 2 by 3 is the probability of success. Q is 1 by 3 in this case. And so let's see what we get. So there are, in 7 trials, there are 102 to the power 7, 128 possible outcomes. The number of possibilities for 4 heads among these is C, combination 7, 4. And 7 trials are independent, meaning that the coin doesn't remember which side was up last time you flipped it, so it doesn't have memory. That means the probability of each of those outcomes, that we have 4 heads, 3 tails, is P to the power 4 times Q to the power, P to the power 4 times Q to the power 3. And how many different ways can that happen? Well, that can happen in, like I said, C7 4 ways, and that's why we multiply this over here by C7 4. You expand that and you get 560 over 2187 after you expand all of this. So C7 4 is, of course, 7 factorial over 4 factorial divided, and 7 minus 4 factorial, and then you open up those two fractions, 2 to the power 4, 3 to the power 4 times 1 over 3 to the power 3. Evaluate that whole thing, it comes out to 560 over 2187, or 25.61%. So let's use S over here as shorthand for success, F as shorthand for failure. Like before, we have a probability of success P and a probability of failure Q equal to 1 minus P. What is the probability of 2 successes in 5 independent Bernoulli trials? So let's look at a possible sequence, one such as SS, FFF, 2 successes, 3 failures after that. What is the probability that we will generate exactly this sequence? Well, a sequence SS, FFF. Well, what's the probability that the first one will turn out to be S, a success? It's P. The second one also P. Third one being an F, probability is Q. Fourth one being a fail, an F, also Q. And last one being an F, also Q. Remember, it doesn't matter what happened before, or even before that. A coin doesn't have any memory. So that's why this word independent Bernoulli trial. One trial doesn't have anything to do with what happened before. So that gets us to P squared Q cube. Here's another sequence. Failure, success, failure, success, failure. Now, if you can see that, we can compute the probability of this one coming up. Q, P, Q, P, Q. Simplify, rewrite that a little nicer, and you get P squared Q cube, Q cube again. So it turns out that it doesn't matter in independent Bernoulli trials, it doesn't matter in which order the successes and failures happen, all that really matters is how many times you see successes, how many times you see failures in how many trials. So whether it is this specific sequence or in this specific sequence that the two successes show up in 5 trials, the probability of each of these trials or each of these sequences showing up is equal p square q cube. And that brings us to the question, how many possible sequences are there? In other words, how many ways are there to pick 2 items from a list of 5? We know we have a formula for that. We can use combination again. C5 2 ways, which if you expand that, evaluate it, comes out to 10 ways to do this. So there are 10 possible sequences, each of which occurs with a probability p square q cube. And for that reason, the probability of any such sequence occurring when performing 5 Bernoulli trials is C52 p square times q cube. In general, for k successes in n Bernoulli trials, that gets us to this expression, which is, of course, closed form expression of the Bernoulli function. Now, in some experiments, already saw, we would like to assign a numerical value to each possible outcome, and saw that right at the beginning of the chapter when I introduced you to the term random variable. And we do that in order to facilitate mathematical analysis of experiments, and for this purpose, that's why we introduced random variables. Haven't done much with random variables up to this point, but you see where they fit in between the other related terms: outcome, sample space, experiment, trial. So a random variable is a function from sample space of an experiment to a set of real numbers, that mapping from an outcome to a number. A random variable assigns a real number to each possible outcome. And sometimes, like I said, that mapping is so tight in some experiments, like when we talk about the roll of a die. The outcomes themselves are kind of already numbers. Although the random variable that you define could map any of those outcomes to any numbers if it makes sense to the problem that you're solving. You could map the 1 dot face, you could map that to 10. The 2 dot face, you can map that to 20, if it makes sense to whatever problem you're trying to solve. So there has to be a mapping. That's all. So random variables are, because they're basically mappings, random variables are basically functions. They're not really variables. And they're not random, but they're mappings from results of experiments to real numbers. So, like I mentioned, random variables are typically denoted by uppercase letters. So, let's say X. Let X be the result of a rock paper scissors game. You know the game. Probably seen it in The Big Bang Theory, or a variation of it. So it's a game played by 2 players. So player A chooses one of those 3 symbols: rock, paper, or scissors, subsymbol A, and the other player B chooses his own symbol. Let's call that B. Also taken from these 3 options: rock, paper, scissors. And if the function, this random variable X, if pass it A and B, it'll return one of 3 possible values. 1 if player A wins, -1 if player B wins, and a 0 if there's a tie, which is also a possibility. And these are the rules of the game. If both players pick the same symbol to play, rock, rock, paper, paper, or both players pick scissors, that's when you have a tie. Other than that, scissors can cut paper, so that's a situation in which player A would win. So this random variable x would return a 1. Rock crushes scissors, so that's another situation in which player A would win. And paper can wrap up a rock, so that's another situation in which player A would win. If these symbols were reversed, so rock, paper, that's when they played the opposite way, when the play is exchanged, is reversed, that would be a situation in which player B wins, so -1. Paper gets cut by scissors, so that's a situation in which, again, player B would win. And the scissors of player A would be crushed by the rock of player B, so that's another situation in which player B wins. And in these last three situations, this random variable returns a -1. So once we have defined a random variable like we just did for our experiment, we can statistically analyze the outcomes from this experiment. For example, we can ask what is the average value, called the expected value, of that random variable when the experiment is carried out a large number of times. So expected value is kind of like a fancy way of saying average. So can we just calculate the mean across all possible values of the random variable and that's it? And the answer is no, we cannot. Because it's possible that some outcomes are more likely than others. And we've seen that with the example of the loaded, the biased die. So what do we do? Some outcomes are more likely than others. So for example, let's consider the possible outcomes from an experiment are two numbers, 1 and 2. But the probabilities with which they occur are 0.1 and 0.9. Question: the number halfway between 1 and 2 is 1.5. Is that the expected value of this experiment? From this experiment? Well, expected values are defined for random variables, but is that the expected value of this random variable? The answer is no. 2 is much more likely than 1. Remember? Look at the probability values. The probability that 1 occurs is only 0.1 or 10%. The probability that 2 shows up is 0.9 or 90%. So the average should be larger than 1.5. It should be closer to 2. So instead of just picking the number that's midway, or simply computing the arithmetic mean, what we do is we compute the weighted sum of all possible outcomes, which means each outcome, in this case 1 and 2, is weighted by its probability. It's multiplied by its probability before adding them to a sum. And here's what that looks like. So we have outcomes 1 and 2, two possible values of the random variable, and we multiply them by their respective probabilities. So the probability of 1 showing up is 0.1, the probability of 2 showing up is 0.9, so we multiply them together, and then we add them up. And then we get 0.1 over here, and we get 1.8 over here. Add them up and you get 1.9. 1.9 is the expected value of the random variable of this experiment. And here's all of this with proper notation. So expected values are defined, like I said, for random variables. In this case, the random variable is x. We denote the expected value like so. So E is also called the expected value function. You pass it a random variable as argument, and here's how you compute the expected value. A value that random variable may take, or x may take on, multiplied by the probability with which that particular value will occur. And then we add those up for all possible outcomes, all possible values that x may take on. So let's consider another random variable x, and it is equal to the sum of the numbers that appear when a pair of dice is rolled. So what are the possible sums that we can see when a pair of dice is rolled? So obviously there are 36 possible outcomes. So you can get 1, 2, 3, 4, 5, or 6 on die number 1, 1, 2, 3, 4, 5, or 6 on die number 2. You can see there are many different, 36 different possible combinations of what you can see. But then ultimately the random variable x is defined as the sum of those numbers, and there's only 11 possible sums that you can get. Smallest sum you can get is 2 when you get 1 and 1. The largest value is 12 when you get 6 and 6. And in between you get every other number, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's the range of random variable x. So are the 36 outcomes equally likely? Well, the 36 possible outcomes are equally likely. Are the 11 values of x equally likely to occur? And the answer is no. Because many of these fields that you see in here will add up to the same numbers. So for example, 2 can be obtained as 1 plus 1. 3 can be obtained by 1 plus 2 or by 2 plus 1. 4 can be obtained by 1 plus 3, 3 plus 1, and also 2 plus 2. So there are 3 different ways you can get 4. There are only 2 different ways you can get 3 as a sum, and there's only 1 way you can get 2 as a sum. So each of the values that x can take on will have a different probability. And here are those probabilities. So there are, like I said, there's only 1 way to get 2 for the sum. There are 2 ways to get 3 for the sum. There are 3 different ways to get 4. There are 4 different ways to get 5. 4 different ways to get 5. 5 different ways to get 6. 6 different ways to get 7. But then again, only 5 different ways to get 8, 4 different ways to get 9, 3 different ways to get 10, 2 different ways to get 11, and only 1 way to get 12. Based on that, you can come up with the different probabilities for each outcome between 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. To find the expected value, Well, just apply the formula the way we saw it. So expected value of x is outcome multiplied by its own probability. Next outcome multiplied by probability which it will occur. 4. Outcome multiplied by the probability with which it will occur, and so on until cover all possible outcomes. Add all of this up and you will get the value 7, a nice whole number. This means that if we roll the dice many times, sum up all the numbers that we get at the end of each experiment, sum them all up, do it 1,000,000 times, add up the million sums, and divide by 1,000,000, the expected value of that result will be 7. That's what the expected value means, the average. Okay, so if x and y are random variables on a sample space S, then the expected value of x plus y is equal to the expected value of x plus the expected value of y. And this can be further generalized to n random variables. The expected value of the sum of n random variables is equal to the sum of expected values of each random variable. Same thing. If you have a linear function on a random variable like this, where a and b are some real numbers, you are allowed to, and you want to find the expected value of this function of a random variable, you can take out the constant like this. You can take that out of the expected value function. You can even move anything being a constant being multiplied with a random variable. You can move that out of the function. X, however, has to stay inside. Okay, so knowing this theorem, we could now solve the previous example much more easily. So let's say x1 and x2 are the numbers appearing on the first and the second die respectively. So each die has an equal probability for each of the 6 numbers that appear. So for that reason, expected value of x1 is equal to the expected value of x2, which is just 1, 2, 3, 4, 5, and 6 each multiplied by 1 by 6. This is a little oversimplified over here. And expected value will be 7 by 2. And since we're interested in expected value of x1 plus x2, and now applying that theorem that expected value of sum of 2 random variables is equal to the sum of expected values of the individual random variables, 7 by 2 plus 7 by 2 is just 7. Much faster, much less math. And we can use our knowledge about expected values to compute the average case complexity of an algorithm. So, for example, let the sample space be the set of all possible inputs, A1, A2, up to AN, and it should be a subscript, and the random variable x assigned to each AJ, the number of operations that the algorithm executes for that input. So for input AJ, probability that this input incurs is given by this function over here. The algorithm's average case complexity then is x of AJ times probability of AJ. So basically just an application of the expected value function. However, in order to conduct an average case analysis, you would need to find out the number of steps that the algorithm takes for any possible input and the probability for each of these inputs to occur. For most algorithms, this would be a very complex task. So we usually just stick to worst case analysis. Okay, So, definition. So, random variables x and y on the sample space S are independent if the probability that one variable takes on a specific value, say R1, and the probability that the other variable y, random variable y, takes on another value R2, if that is equal to the probability that x takes on the value of R1 multiplied by the probability that y takes on the other value, R2. So if this is the case for all possible values that x and y may take on, if that holds for all those combinations, then we say that x and y are independent random variables. And equals the product and the probability that two outcomes occur jointly for x and y, that equals the product of the probability that x takes on one specific value and y takes on the other value for any of the numbers that x and y map to. Now, an example. Are the random variables x1 and x2 from the pair of dice example, are they independent? Let's see. So probability that x1 takes on any particular value is 1 by 6. Probability that x2 takes on any particular value is also 1 by 6. The probability that x1 takes on some value I and x2 takes on some value j, remember, each combination of outputs had a probability of 1 by 36. You can already see where this is headed. Yes, this holds. 1 by 36 is equal to 1 by 6 multiplied by 1 by 6. So yeah, x1 and x2 are in fact, from that experiment, are in fact independent. If x and y are independent random variables on a sample space, then we can, from that, we can write that, we can conclude from that this expected value of xy is equal to the expected value of x multiplied by the expected value of y. Note that this is true for any x and y, whether they're independent or not. What we just saw up here, expected value of xy being equal to the product of the expected value of x and the expected value of y. For that, x and y need to be independent. So, always, sometimes. So let x and y be random variables on some sample space, and each of them assumes the values 1 and 3 with equal probability. So expected value of x is equal to the expected value of y is equal to 2. Equal probability, right? So expected value of x plus y is 1 by 4. Quarter probability that we'll see 1 and 1. Quarter probability that we'll see 1 and 3. Quarter probability that we'll see 3 and 1. And a quarter probability that we'll see 3 and 3. Solve this and the answer comes out to 4, which also happens to be expected value of x equal to expected value of y, 2 plus 2. Now, let's try it for e of xy. So, e of xy, quarter probability that you see 1 and 1, so multiply 1 and 1 in here. Quarter probability that we see 1 and 3, but we're multiplying 1 and 3 in here. Quarter probability that we'll see 3 and 1, but we're multiplying 3 and 1 in here, right? And a quarter probability that we'll see 3 and 3 in here. do that, and you get 4, which also happens to be equal to expected value of x times expected value of y. So because of that, x and y, yes, are independent. Now let's assume that x and y are correlated in such a way that y is 1 when x is 1, and y is 3 whenever x is 3. That means expected value of x plus y is, well, when 1 is 1, when x is 1, y is 1, when x is 3, y is 3. Only 2 possible cases. There's no situation in which x can be 1 and y can be anything different. It can be 3, or when x can be 3 and y can be 1. So there are only two possible cases here. Probability that that happens is half and half, which makes all of this half times 2 plus half times 6 comes out to 4. 1 plus 3, 4. Which is equal to e of x plus e of y. Fine. But let's try out the other one. So half and half, the probabilities of the 2 possible joint outcomes. And in here we have 1 times 1, in here we have 9 times 9. Oh, sorry, 3 times 3, meaning 9. This. So this becomes 0.5 plus 4.5, which adds up to 5, which is not equal to e of x times e of y. Which means x and y are not independent. Now, the expected value of a random variable is a very important parameter. An expected value is basically like, it's a summary, but it's a very limited, it's an important summary of the distribution of a random variable, but it's only one type of summary. It's one way, one limited aspect of it. Another important parameter, another property of a random variable is how spread out, how much variation there can be in the outcomes from an experiment, the values that a random variable may map to. And for that we have a different statistic, a different metric. And that metric, the metric we're interested in right now, the one that tells us how widely distributed the values of a random variable are, that is called variance. And this is the mathematical definition of variance. So we have probability, we have the same probability term over here, but in here it gets interesting. We are basically subtracting from the outcome, from the value that the random variable may take, we're subtracting from it the mean. So we have the difference between mean and average value and a value of random variable that it may take, and we square it. And we weigh that by the probability with which we may see that particular value for the random variable, in this case, in here, S. And we compute this for all possible values in the sample space, and then add that up again. I know this is a little strange. I'll edit that in the slides, but over here it uses V of x to denote variance. Another common notation is variance of x, like this, or another notation is sigma square of x, something like this. And actually, even more common than that, something like this. X, the name of the random variable, just in the subscript. The standard, the variance usually gives you a very large number that is off the scale because of this off scale with respect to values that the random variable takes. That's because of this square operation happening in here. What we're basically doing is we are interested in the difference between the value that a random variable takes and its average value, squaring that because the difference between the two can be positive or negative, right? So in order to make sure that the differences, the positive and negative differences don't cancel each other out, we take the square to make sure that this difference term is always positive. And then we weigh them by probabilities. The standard deviation of x is simply the square root of v of x. So it's denoted for that reason. It's denoted by simply sigma of x. So basically skip this square term. Or you can also think of it as the square root of v of x. Same thing. Okay? Just like these two are the same thing. Okay, some useful rules here. If x is a random variable on the sample space, then the variance of x is equal to expected value of x squared minus the expected value of x squared. Okay. I have to tell you though that a lot of the stuff that we're doing in this chapter, it's usually covered over a much greater period of time. So this is the way we're covering in this course. It's kind of rushed, but yeah, that's what it is. But we usually spend a lot more time getting from the definition of a random variable to this particular equation. And we usually don't just throw it at students. Usually we go through, we actually derive this particular expression, this particular equation. So if x and y are two independent and random variables on a sample space S, then the variance of x plus y is equal to the variance of x plus the variance of y. It's also worth noting. And if you can generalize that, if you have n random variables and they are pairwise independent, then the variance of the sum of all n random variables is equal to the sum of variances of each of those n random variables. And that's the end of this chapter number 7.